Here we have a problem with a distributed load that we're trying to find the concentrated force and the location where it acts. We're given the concentrated load at 4x minus 0.7 x squared. Now if we find our concentrated force, right, if we call it R, would be the integration over the area, just the area. If we want to have x bar, then we'd have x bar times R over R. R we already had up there, so x bar R, that would be integration of A of x tilde times dA divided by R. All right, so that's all that we have to do. These two relatively simple integrals here. So we'll start by figuring out what dA is. Right? First thing we're saying, I want to say what dA is. Well, let's sketch ourselves a dA in here somewhere. This is our dA, and that is dx. And this height here is, of course, just, in our case now, w of x. So we can say this would be, oops, it's not red. Oh, that looks, let's rewrite that w of x there, it looks a little strange. W of x. Now let's get to black. So that would be w of x times dx, or in our case, 4x minus 0.7 x squared. Oop, that should be a 0.6. Apologize, my notes are wrong. I changed that value later on. So let's stick with the ones that we have in the notes. 0.6 x squared dx. And then the other thing we need to know is our x tilde here. X tilde would be the distance of the centroid. Oop, wrong size of pen. Centroid. Right, this is our case. That's of course just x. So x tilde is equal to x. And with that, we can just go ahead and do our integrations. So we can say our concentrated force, the magnitude, is, we said, A dA. In terms of x, we go from 0 to 5. And we said dA was this right up here, right? Was 4x minus 0.6 x squared dx. So all we have to do is solve this. All right, so that would be, if I go to squared, I can do it 2 x squared minus 0.2 x cubed, 0 to 5. Right, that's just 0.6 divided by 3. So that would be 2 times 5 squared minus 0.2 times 5 to the third. And that comes out to be 25 kilonewton. So that's our concentrated force. Now our x bar times A is what? X bar times R is equal to the integral over the area of x tilde dA. We said we're going from 0 to 5. X tilde is just x, and then our function, 4x minus 0.6x squared dx. That means we need to pull in that x, so we have 0 to 5 of 4x squared minus 0.6 x to the 3 is equal to 4/3 of x cubed minus 0.6 over 4 x to the 4, 0 to 5. So that'd be 4/3 times 5 to the 3 minus, if I divide that, be 0.15 times 5 to the 4. And if I plug that in, I don't get that great of a number. I get 875 over 12 kilonewton meter. So now if I want to get x bar, then I'd have x bar times r over r. So 875 divided by 12 kilonewton meters divided by 25 kilonewton. That gives me 35 over 12 meters, or 2.917 meters. So there we go. So if we look up here, now we have too much in there already. Maybe we'll just overlay with blue. Oh, well, maybe we're not kind of, so 2.5 would be here. So my R would be maybe somewhere here. Let's say R equal to 25 kilonewton and 2.917 meters is where it acts. All right, with that, we have taken a pretty complex looking distributed load, and we found the resultant force and where this force acts.